always look at it to make sure the right file's submitted.
I know, I'm a little paranoid.
So, before we go to chapter 3, I want to close chapter 2, the hydrostatics with the buoyancy. If you have an object that is fully submerged, like a cylinder with a basket, the law of buoyancy says that there is going to be a force coming from this fluid acting on the object. Now that value of force is equal to the rate of displaced water or fluid. You see, this is Archimedes' law. We talked about it last class, like 2,000 years, more than 2,000 years, 3,000 years, 2,500 years old law, which assumes perfectly, and you proved it last class. Now, this is a summary of this. Say the force that is fluid applying to this object, so this object, right, is equal to the weight of displaced fluid, not the weight of object. The weight of the amount of fluid that is displaced. It's not that if I take it out, the water level goes down. And if I submerge it, the water level goes up. How much this water or fluid is displaced? The weight of that is equal to the force acting on object. Right? So, if don't make a mistake that if I give the density of the object and the density of fluid, now what's the weight of object? The weight of object is simply mg, mass of object, right? M object times g. What's the mass of object? Rho object times v, volume of object, is the density of, is the mass of object. Y, density is equal to mass per volume. Right? So if I solve that for m, I get rho v. So rho object times v times g. So look, I can group this together, rho and g. What was rho times g? Gamma. Gamma object times volume of object. This is the weight of object. This is not the F. One mistake they will make is they use the density of object. Now, the Archimedes law say F is equal to the weight of displaced water. Right? So you can use how much water is displaced. Well, I don't know the weight of it, but I know the volume of it. Right? Later on, we studied something called continuity equation. Because the fluid is incompressible, you can't compress it. The amount of displacement here, the volume is exactly the volume of displacement. So you know the volume of displacement is V. All you need to do the same thing, but here with the density of fluid. So the only difference is F equal to gamma fluid times V. And we prove this mathematically. Right? So now in the midterm, I may give not this simple thing, I may give something like this shape and say, well, we got something like that, extruded trapezoid, and then I give dimension of that. This, for example, 3, 2, and 1, something like that. And I say, for example, 3. I say from here to here is 4 meters. And then I say find the resultant force on this in the Y, the buoyancy force. Or I may give this thing, what's the minimum weight for that in order to be completely suspended in water? That means that weight should be equal to the buoyancy force, right? Things like that. I'll make you a question like that. Now you know that this weight is not relevant to that, this height or depth of submerged water, right? Because the buoyancy force only depends on the density of fluid and volume. So all you need to do is to find the volume of that, right? How do you find the volume? Well, we can find the area of this, right? How do you find the area of that? Cut it up into subshapes. right? There are many ways. Whatever way you do that, I accept if it's way. And then find the area of this, multiply by height, you get volume. I give you density of fluid, put it here, get the volume. Right? Okay. What if it was like this? What if it was not fully submerged? It was like this. What if it was like this? Like, let's say this was 2, this was 1, and this was 3, and this is just a cylinder. See, it say weight of displaced water. So if I just put just part of it into water, what part is submerged?
At 2 meters.
Yeah, at 2 meters and below. So the volume we substitute here is 2 times pi 1.5 square, the area of the volume of submerged. Now another thing I may give you, for example, well this is, I'm not going to give this in the test because it's very challenging, not very, but it requires some thinking. I may say, well, you got a bubble, and it goes up. Why it goes up?
Got more buoyancy than
Because you got a buoyancy, and this thing flexible is just an oxygen inside water, right? So it can expand, right? So obviously, if you just start at a point with a diameter like 1 inch at the point, then when it goes up, what happens to it?
It expands.
It expands. But we don't know how much it expands, right? I may give like, maybe like a challenge. I'm going to soon post like waivers, but challenging waivers, not in class. Like you have 2 days to solve that. If you do that, you get a good waiver. And home waivers. But they're really challenging. And if you ask somebody on internet, hey, can you solve this for me? And I take you to office and I ask questions. So do not try to cheat. You know me. I want to make sure that you believe yourself. But if you do it yourself, you definitely get a waiver. So for this problem, I say, well, this starts at this point of height, let's say 10 foot, right? And the initial diameter is 1 inch. And then we release it, and it just goes up, right? Perfectly from the buoyancy force. There is no flow coming in because the flow of the main water flow can agitate it, right? And turbulence, other perturbation. There is no perturbation, perfectly buoyant. And then I say, find the relation between the diameter of that and the height. So how does it expand? Is it going to expand linearly? It's not expanding linearly. It's a very nice, beautiful, complicated relation. It's called analytical methods. We will talk about it today. Now, I will post waivers. I'll probably work on that, make a waiver out of it. But I post all the waivers like use computer programs. Here we have ANSYS, we have some other software the university paid for it, but a lot of money. Right? Simulation software. Why not using it? If the university paid for it, you paid for class. Why not using it? So I may put a waiver. You know, this problem, you see the dam problem I put in the homework number 3. Just use a computer program, like ANSYS, any commercial program, and simulate it. So draw in SolidWorks, draw that auto mechanism, draw the wall, right? Put hinge component, connect it together, so you get a complete mechanism in SolidWorks. Import it in flow solver, put flow behind it, and say run, and see how much force you get in that weight. You see, if the weight is small, what happens? It goes up. If your weight is just too high, it goes down. At some point, you get balance. So that's going to be a waiver. If you can, it's totally optional. But I promise, it's going to take you 1 week to do that. More than 1 week. Even if you do YouTube, just to how to set it up, right? How to use that software, because you don't know anything about that software. You have to start from scratch. Well, you have to start at some point. Well, this software are very important. If you want to get a job in a company, they say, do you know that software? And you say, well, I only can integrate. I'll go and pay my fluid mechanic. Oh, I don't know that software. And they say, oh, you're very welcome. Right. Well, if you know the software, right, and say you see, we can show you like a portfolio. Like, look at this figure, I did this. Look at this project, I did that. Look at the other. And they don't ask you if this is a class project or meter waiver. They think that this was a big, like a capstone project. Right? And you may get included just because of doing that. Right? So I just want to give you motivation for doing this. So let's go to chapter 3 now. Chapter 3, after this point, we're done with the statics. So after this point, our problem, this water is always moves somehow. So we're not in the water is not in perfect equilibrium. No hydrostatic, it's moving. And now, in order to explain, in order to analyze, I wish they had another key on the other side. We could just, it's just a single symbol. Just dim the light from here. All right, so in order to analyze the fluid, you gotta have some sort of equations. All right, otherwise we go back to the Stone Age, and there is no way to design this thing except to. There is no way to design this thing except to build it, like experimental. That was the old ancient old-fashioned method. Now, if you want to do it on paper, analyze it, or by computer, you gotta have some sort of equation, right? So in order to develop that some sort of equation, we first need to understand some terminology, some vocabulary, some definition. Alright, so I'm going to go over those before we actually get into those equations. And those equations called Navier-Stokes, I mentioned in the first class, maybe second, I think it was the second. But those Navier-Stokes, if I show them to you right now, we may freak out because it requires some preliminary things to be covered. Well, at some point you totally understand it, and you should be able to work with them. For a special simple problem, solve it, simplify, which term goes to 0, which term is non-0. You have to have a good intuition about all of them. So the first thing we start is, we already talked about the regime based on velocity. This is some sort of classification of the fluid motion. As I said, the fluid is all, after this point, the fluid is moving, so you have the velocity. And we've already talked about the streamlines, that at every point, if you have a velocity vector, you feed the streamlines to that, you get the pattern. And we, based on the motion, you can classify fluid into laminar flow and then turbulent flow. The one on the left, laminar flow, as you can see, yes.
Is it always one or the other?
Yes, there is a transitional. There is a third one called transitional, but when you are in transition, you have to decrease the velocity to go back to this. You can't, in the same time, you can't be turbulent or transition. Some part of the geometry may be laminar, that has a smaller velocity, but the one that has larger velocity, like this, may be turbulent. So yeah, locally it may be different, but we're talking about just this, imagine this infinitesimal part in space. We're talking about local. So the turbulent one, you see the velocity get a little bit crazy, you got fluctuation, and the pattern is complicated, and this was a very weird thing like 50 years ago, but nowadays they also model that using good math, good software, and it's not really a big problem nowadays. It's modeled very, very well. But still there is a little bit of space for research, but today we have good tools. Next problem. So as you can see, I mentioned there is a laminar flow, the one on the left, there is a turbulent flow, that is you have fully chaotic fluctuating pattern for the streamlines, and then there is something between transitional flow, and this one is the hard one. Because in some local, as I mentioned, you have laminar flow at some points, at some point you have turbulent flow, right? So you don't know which one. So this is a classification based on the speed of fluid. Later on, we define something called Reynolds number, that is a combination of viscosity and speed. It's a dimensional factor that combines all these into one parameter. Right? So, as you can see, this is a laminar. If this is a pipe and the flow is going from left to right, you know that from the law of the boundaries, we mentioned that the molecule will stick to the wall on both top and bottom if the wall is viscous bottom, right? So you have viscosity. Now, in the laminar flow, you have this pattern, the parabolic pattern is beautiful, it's smooth. But in the turbulent flow, you get a pattern like the one on the right. Now, if I ask you to find the shear stress at the right, you say shear stress is what? U times du dy. What's the du dy here? Okay, the slope is way higher than the slope here. See that? So if the slope is way higher, what can I say about shear? The shear is way higher on the right. Compared to this. That's
shear between the fluid
and the water. Right. So one of the characteristics of turbulent flow is higher drag. So let's say, in fact, the guy who discovered this for the first time, he was an Englishman called Reynolds, Osborne Reynolds. And the way he discovered it, he didn't have anything to make a photograph like that, but he had a long pipe, and he had a pump. He tried to pump the water in the pipe, and everything was proportional when he was like in laminar, like a speed was low. But at some particular speed, he got a crazy behavior in the pump. It was almost breaking. It could not push the water in. And that's the time that you get turbulent. Because you need a lot of resistance, you need a lot of power to conquer that resistance. So he discovered a relation between the power of the pump and the diameter of the pipe, and then he developed something called Reynolds number. And he published that in like, I think it was 18 something. Before even Navier-Stokes equation was right. This is a long time before that. And then one of the most important things is fluid mechanics is Reynolds. Yes?
It looks like on the right graph, there's more area under the graph than the left one. Are they like the same size? So there'd be more like volume of water being flown through in the...
Yeah. So you see the core velocity, you have higher core velocity here. So as we talk about average velocity, we talk about something called flow rate. We talk about that later, not right now. We're going to go step by step. We talk about all those things soon. Right? So next is called classification based on dimensions. So if you see a pattern, you see this pattern, if I have a pipe and you go flow inside that pipe, the pattern, if you look at it from the side, you only see variation in the Y, right? And also variation in the X. Because this geometry is converging also, right? So the amount of velocity not only changing in the X, right? What's your intuition is telling you? Is it going to be higher the average velocity here or here?
It'll be higher the smaller it gets.
Yeah, that's right. You see, later on, if you make it to last chapter called compressible flow, which I don't think we can make it there, because this is two core, fluid mechanics 1, fluid mechanics 2. Right? But if you make it there, we show that in compressible flow is opposite. It's totally non-intuitive. So when you have conversion nozzle, the velocity decreases and the pressure increases. But now what we do, everything we do here in this class is called subsonic. That means the flow, the speed is small, below the speed of sound, and the flow is not compressing, right? In that case, yes, your intuition, right? The more we go, the velocity increases. Why? Because the area just try to push that fluid into the smaller area so you have more velocity, more flow velocity. But what I'm trying to do right now, this classification right now is based on the dimensions. So you see the x dimension I have changed. In the y dimension, you see I have also changed. So it's two dimensions. You see it's a two-dimensional because it was x and y changes. Now if this was a constant cross section, nozzle like that, how many dimensions do I have? One. If there was no drop, no change in the x, it would be only the change in the y. Now, similarly, you see this is just one dimension. Right? Now let's say even this was like invisible, there was no viscosity in the wall, the molecules are not attaching to the wall, then the dimension is what? The dimension is non-dimensional. There is no dimension, everywhere velocity is same. Right? These are, in fact, they do things like that, they call level of approximation. These are different level of approximation. The more you include, the more accurate result you get. But it's more expensive, the more dimension you have. Right? Now, let's talk about the streamline. We already had a session for this, what's the streamline, and I'll show you the videos. I'm pretty sure most of you guys have watched the videos. So the streamline, the way you create it, at any point you get a tangent line for every point in the field, and then you connect this tangent line together to get the streamline. And some of this streamline may end at one point, so it's like a singularity. There is not always, infinity, right? They may end at a point like here, and that point called stagnation point. That's the point that the velocity is 0. Other than the stagnation point, there is a singularity point. The streamline always, for example, if you go infinitesimal about the stagnation point, you go all the way around the cylinder and then you exit. Right? So these are the streamlines. Next thing I want to say for incompressible flow, I don't even want to say compressible and incompressible because this class includes incompressible. Right, so let me drop that here. You can see that in this kind of flow is the velocity is faster on top of the cylinder. Why? Because you're pushing into a smaller diameter of the streamline. So one way the streamline are used, they are used to see how much the velocity variation you have. And later on we have something called Bernoulli equation, which basically quantify into this pattern into an equation called the Bernoulli equation. And we use it a lot. Now, another thing you can get from a streamline, like for example, if I give you the velocity field, you should be able to give me the equation for the streamline. And vice versa. If I give you the streamline and I say give me the velocity field, you can do that. So how do we find the relation? One way is just to draw your U and V components. You see that? This U and V component of velocity. Now there is a W, the third component, which is that it doesn't draw it because it makes the drawing very messy. So one way is to say, well, look, compare that to the tangent line. This is streamline. You see that? If you zoom on the streamline from the last slide, then instead of curved line, you get just a straight line at any point. Now look at this triangle in the streamline. The ratio between dx and dy is equal to the ratio between u and v. So from that triangle, if you say that those triangles, this green one, this one, is similar to this triangle, the right one, you can write this equation of ratios. Another way you can write the equation of the streamline is to say, just to use the definition of velocity. The definition of velocity is what? There is always in this course, there is always at least 3 or 4 different ways to do the same thing. So
Distance
always,
over time?
yes,
Distance over time?
yeah, distance over time. So always try to go over different views for the same thing. So distance over time, derivative of the distance vector over time is velocity. This was what? Distance vector. You remember vector studies? Yeah, distance vector. So if I write a component of that, you have 3 components in 3D space. U, which is the V. If you write V velocity vector as Ui plus Vj plus Wk, so you have three components. U is what? Dx dt. V is what? Dy dt. W is dz dt. Right? Just the differential velocity. Distance over time. That's just infinitesimal. Now, solve for t. Here, in this equation, you can write dt is equal to what? Dx over u. Right? And here, the same dt, because dt is same, is equal to what? Dy over v. And then here, the same dt is what? dz over w. Since dt is equal to same, so you have what? You can write dx over u is equal to dy over v equal to dz over w. The cohesions of the streamline is called the cohesion of streamlines. That's exactly the same equation you see in this slide. But this is just one component of that. This is just grab this part and rearrange it. Bring u here, v here. You get it exactly that. Right? So let's proceed to the next slide. What are the methods of analysis? Again, if you were like 100 years ago, 200 years ago, first of all, nobody cared because there was no industry, there was no machine, no trains, no motion, right? Nobody cared. But nowadays, you have this thing, you have to design them. One way is to do experimental method. This is the old-fashioned and yet the most robust method still. So everything you do, let's say analytical, CFD. What's CFD? Computational fluid dynamics. The last word, computational. Everything you do, you have to match it with the experiment, right? At some point. So the first method of analysis is called experimental method, and these methods are huge. Like the category of experimental method, they do crazy things. Usually when we go to mechanical engineering department, everybody talking about computer methods, right? Nowadays, but there are good schools, big schools, and industries, they do only experimental studies. Now, experimental method one is called shadow graph method, and this goes through different things. Schlieren photography, so they shed a light on the flow, and based on the variation in the density, they can get velocity by just taking videos. We have one of these machines downstairs in the lab fluid, and this is a supersonic unit. Now we talk about it later, you can get shots. So the last method of what was released is called PIV, particle image velocity method. And this method is basically what they do. They have tiny little particles. They're almost massless, and they put it in the water, and then there is a camera. There is a high resolution camera that tracks every single particle in the flow. Right? So you get a streak lines, and based on that video, you can post-process later to get velocity field. And if you get velocity field later on, see using Bernoulli equation, you can get pressure. So experimentally, you can compute all these parameters. And good news is right now, starting from the summer 2022, we are trying to bring PIV method into our labs. Successfully, we had one project by Dr. Shri. He started it, and we are utilizing one industrial PIV station in one of our labs. Hopefully, by next semester or next year, we have this fully integrated into our lab, so we use PIV to find velocity field in one of the experiments. The next level of analysis, analytical. An analytical method, again, is an old-fashioned, like 100 years ago, but it requires a lot of mathematics. And some of the problems you cannot solve analytically in fluid dynamics, especially in 3D. Because Navier-Stokes equation is not solved analytically yet. The complete general three-dimensional Navier-Stokes is not solved yet. Nobody can solve it analytically. But you can simplify and add some assumption and make it lower dimensional and apply very advanced mathematics to come up with some analytical without even using a computer. The last one is computational method, including CFD, and there are some other things, computational acoustics, CAA, and computational solid mechanics, with fluid structure, interaction, FSI. Lots of different things. What these methods are based on, again, Navier-Stokes equation, what they use computer to discretize it. How do they do that? Well, I want to talk about that later. Let's go to the next slide. This is an example of the experimental. You shell graph, you have variation in density, take image, and based on that, you can find a streamline, a straight line, and find the pressure drop. Example of analytical technique, this one project we have with TVA, and this is a very complicated project. It's in a crane and nuclear facilities, TVA cranes, and they had full 3D mechanism for the crane that is connected to this cylinder. They call it dynamic shock absorbing cylinder. And then you have fluid, you see inside that piston, there is a fluid. And let's say one of the cable in the crane, there are double safety mechanisms. One of them breaks. The other one, you see, this goes to one end, this goes to another cable. If one of them breaks, let's say we break it here. The other one takes the load, but this cylinder damps down the dynamic load factor. So the fluid here, this valve opens, and it goes to the reservoir. And this is really, if you want to do this computer, you have to have a computer program which you couldn't find that solves both solid mechanics, dynamics, the moving pulley system, and also fluids simultaneously. So couple all of them. We could not find any. So what we did, we solved this analytically. We solved it analytically, and the solution is basically this is a part of Navier-Stokes solution. We did a lot of derivation on drop that, but this is just what we're going to do in this class, but not exactly the same thing, very simplified version of that, right? So this, you take a control volume, just like that, you apply equation of Newton or Navier-Stokes equation, and then you add a lot of simplification things, and then you come up with this second order ordinary differential equation, which we solved it. That's the solution. And when we did that, nobody believed it from TVA. They said, well, we're not here to look at this. Give us the data. So what we did, we plot the data and said, this is the dynamic load factor. You're safe. Don't worry. The dynamic load factor was in the before the threshold. And they said, no, we're still, this was very complicated. We don't believe these equations are going to work. So what we did, we built the experimental setup for that, and we measured. We measured the dynamic load factor, and here is the result. The result are, as you can see, this is the dynamic equation for termination velocity. The result are, this is the experiments. You see this line, this is the experimental result, and the dashed line is our equation. It's matching almost perfectly. So this is called analytical method. It's called analytical. It's very seldom these days you see analytical method, but if you have your handbook, you see all those complicated relations in the handbook, tabulated in the handbook. Those are derived using analytical equation. Now we're actually in the process of publishing this in a handbook. So this is going to be added to a handbook. Another thing, example of computational method. So let's say you have a flat plate, and if you have a flat plate, here, let's say you have a flat plate, and then flow is coming here, right? Later on, you say if this is viscous, you have something called boundary layer. So you develop a velocity profile like that. That is zero in the water, like that. 0 in the wall, and then you see, and from the tip, this is the tip of the plate. The velocity is 0, and then the more you go, the boundary layer develops. You see, it goes from 0 to some termination velocity. Now this is from my code, I wrote it from scratch, and this is equal to the fluent code we have here. And with all the conventional, but this three-dimensional code just does the same computation, and it's very accurate. Another computational method, this is the wing of the aircraft. Let's say this is your aircraft, and that's your wing, right? If you cut it, if you section it, you see it here, you see only the two-dimensional, call it airfoil. Airfoil. And that's the airfoil. It's just a cross-section of the wing. Now if the flow goes here, if you are below the speed of sound, everything is nice and smooth, but when you go near the speed of sound, you have a shock wave. This is shock wave. In the videos, YouTube videos, you have seen this aircraft coming in, and there is like a fabric around the aircraft, like a, like a smoky pattern, like very complicated, like a cone. That is shock wave. So using Navier-Stokes equation, this slide to show you, we can do shock wave. What you can do it analytically, you have to do it by computer. How do you do it by computer? We cut this. In fact, the way this is set up, every part of this is decomposed into a smaller problem, a smaller part. So this part, and each one of those parts is solved by a computer independently. And when they solve each part, but not fully, part of it, they send message to each other. Hey, I did this. Did you do that? Give it to me. So they synchronize. And then finally, at some point, they converge all together. You remember the computers? Every single one of those is sent to one of those computers. And you saw the blinking thing in the computer, right? They blink because they're doing synchronization. So all this thing, you can do it from here. You don't need to go to system. You can do it from here on the laptop. What you do, SSH. Remote connection to the system from here. And you submit your job, and you can get it. So these are examples of computational techniques. This is another one. It doesn't have to be aerospace. It's a car manufacturing industry. They want to see the drag on the car. Right? How much drag you get. Right? Especially the trucking industry. They want to add something to the back of the truck to minimize the drag. Right? So this is one example from there. They got the streamlines. Quite computational, and you can see a streamline of everything. Now, let's talk about the description of the fluid. The first one is Lagrangian. That means you just see this particle, you just pick one of them, and you just follow it. Follow the particle. You don't stay somewhere. You just follow one of these particles. Wherever it goes, you just go behind it and see where it goes. It's called Lagrangian description. And for Lagrangian description, all you need to do is the position vector. R, Gaussian vector status. Then by taking derivative of that and substituting the Newton equation, F is equal to ma, you get equation of motion. Again, Navier-Stokes equation, but in Lagrangian form. This is exactly what you did in dynamics. Right? Every one of those masses were just particles. Even if you have like a 3D object, you would start with particle and integrate in the Lagrangian, and then you get moments of inertia. So it was solid mechanical distribution. What you start with particle. The other approach is I call it the lazy approach, is Eulerian. That means you say, look at this box, right? So where's the one? Unfortunately, there is no way that it is one. At least what I see here. So you take a box in a space. It doesn't have to be a box. It can be an arbitrary enclosed region. It can be arbitrary enclosed region. And you say, well, you know what? This is not just like a movie, right? When you watch a movie, you don't see out of screen. You only see inside the screen. You say, this is my screen. All the particles coming in, I can see them. But when they leave, I don't care about them. This is called Eulerian approach. And now you can always convert Lagrangian approach. That is a particle that is coming, you just behind and following. And goes into Eulerian approach. There is a relation you can always transfer Lagrangian to Eulerian and vice versa. But we don't do it in this class. In this class, we do Eulerian most of the time. And this guy right here, they call it control volume. And what is the control volume? Control volume is the more general form of control mass. And what is the control mass? Well, we have already used it. You remember when we had a cylinder piston configuration and it was going up or down, the amount of material inside that cylinder piston, and this is the cylinder piston, and there was a gas here. Remember that problem? So this was control mass. Control mass is a mass that is fixed, and you control it. Control mass. It's just a method of analyze. Now, if this piston moves down, we have this control mass shrinking, right? So control mass is always attached to that specific mass, wherever it goes. Control volume is usually fixed. So if I want to take control volume for that, I would just say, you know what, I'm just considering this window, and now if it goes down or up, I just look at this window, I don't follow that. Now, when we derive Navier-Stokes in this class later, we consider general case of control volume. What's the general case of control volume? The control volume that also could be control mass. That means it can move, it can expand, it can even transfer in the fluid. So we use that to derive Navier-Stokes. But usually when they say control volume, they're talking about fixed frame or screen. When they say control mass, they're talking about a certain amount of mass that either expand or compress, and you have to follow it. Right? So here in the Eulerian approach, as I said, it's just exponential values to your screen with the blue region that's in control volume. And these are the particles. Some of them at time t1 are inside that. At time t2, some of them are outside of that. And some of them, the velocity will change inside that. Density may change, velocity may change. You have to take care of everything inside. You don't care about anything outside. So in the Eulerian approach, not only you have to take care of things inside, also you have to take care of things that are coming in and the things that are going out. We call them flux. So in the Eulerian approach, you have something called flux. In the Lagrangian approach, there is no flux. Because you always track a particle. Right? Example one, let's say I give you this velocity field and give me the streamline. What's the velocity field? You have a piece of paper. Velocity field, they give you 6yi plus 3j meter per second. And then they say the flow is two-dimensional, is velocity field. There's only a equation of the streamline that passes through plane 1 and 2. So if you draw your Cartesian xy, this point x is equal to 1, so y is equal to 2, so that point is right here. X is equal to 1, y is equal to 2. Now, we don't know how the pattern is. Right? We really don't know unless they give us the velocity field. And based on that, we want to see the pattern. So what should I do? Well, I use one of those equations. You see, the general equation is what? Dx over u is equal to dy over v is equal to dz over w. It's called a differential equation, right? So let's substitute in it. What's my u? 6y, v, 3, w, 0. There is no k component, right? In the midterm, I may give you the k component, right? Let's put it in here. So you have dx over u 6y is equal to dy over v 3 is equal to dz over w 0. You don't even need to solve it because it's just perfectly 2D. That means in the z direction, we have exactly the same pattern. Nothing is changing in the z. So solve this equation. It's very easy. Probably the easiest form of differential equation. If you have that course, ordinary differential equation, that's the easiest one. So multiply both sides by 6y. Alright, let's do that. So if I multiply both sides by 6y, what I get is dx is equal to 6 divided by 3 to y dy. And then integrate both sides. If you integrate, you get x plus c, constant of integration, is equal to y squared. You may get another constant of integration here, call it C2, right? C2. But look, C2, you can take this here and make it an overall C. Unknown constant of integration, you can add it together. So the question is say, find the streamline. So this is the equation of the streamline. And if you look at it, it has the C, the constant integration. That means you have so many, it's not just one line, it is so many, there are so many lines, right? One of them is passing through that point, 1 and 2. There are infinite lines. Why? Because you got C here. You see that? One of them is passing through that point. So if you substitute x is equal to 1, you see, your y must be what? 2. From that point, you can get constant integration. Let's do that. Put x is equal to 1. So you get 1 plus c is equal to, your y should be 2. 2 to the second power, 4. So your c is what? 3. 4 minus 1, 3. So your final equation get x plus 3 is equal to y squared. What is that? Those are just, okay, drawing off the square root. I'm pretty sure we have drawn this function square root in high school. It's like that. That is the equation of the streamline. That means that if you put a particle here, right, what happens to this particle? This particle goes this way, right? And then the terrace goes this way. That's what happens. All right. I'll see you next class. Make sure you do homework.